Bismillahirrahmanirrahim. Assalamu alaikum, everyone. So today we will solve a recitation problem for chapter 22, electric field. Now let's start. The first problem, we already solved it in class, okay? So we solved this in class. So I'm asking you to solve it again. Now let me start by this problem. So let's read the problem carefully. A 9 microcoulomb point charge is placed at the origin, and a minus 2.25 microcoulomb point charge is placed on the x-axis at x is equal to plus 3 centimeters. The question is, determine the x-coordinate of the point at which the net electric field is 0. So let's translate the data of the problem. This is my x-axis. It's a straight line. So this is x, let me put it in meters. So this is my origin, 0. So at my origin, I have my charge Q1, which is positive, plus 9 microcoulomb, okay? Don't forget it. Now, at plus 3 centimeters, meaning here, at plus 0.03 meters, I have my charge Q2, which is negative, which is minus 2.25 microcoulomb. Now, the question is, at which coordinate x of a point? So at which coordinate do I have 0 net electric field? So let's solve this. This looks like our previous problems, in chapter 21. So if you remember chapter 21, we used to tell you, okay, at which position do I have net electrostatic force is equal to 0? So here I'm asking you, at which position do I have net electric field is equal to 0? So let's plot the electric fields. So for charge, this charge, so it's positive. So the electric field is always away. This charge is negative. The electric field is always pointing toward the negative charge. So let me call this, so it should point away, right? So this is E. So if I'm here in this part of my x-axis, E1 is pointing along the negative x direction. If I'm here, of course, it's pointing away. So E1 should point in this direction. And here also, E1 should point in this direction. And all of them are vectors, by the way. Now, on the other hand, E2, let me put it in green. E2 is due to this point here, which is negative charge. So the electric field should point towards the negative charge. So E2 will be like this here. Okay. E2 should be like this here, pointing towards, and E2 here should be pointing toward the negative charge. Okay. So you see, this is just the physics of the problem. Okay. So when I'm in this part of the graph, in this part, what do you notice? I have both E1 and E2 in opposite direction. But the thing is, you see, Q1 has a larger magnitude than Q2. So basically in this part, E1 will be always bigger than E2. Why? Because the charge is larger and also the distance is smaller. You remember the electric field is just E in magnitude, K, absolute value of Q divided by the distance squared. Okay. So in this part of the graph, I cannot have net electric field equal to 0. Why? You see, E1 will be always larger than E2 in this part. Why? Because Q1 is larger than Q2 in absolute value. That's number one. But number two, the distance from this point to my Q1 will be always smaller. So this 1 over R square will be always larger. So it's basically here, I don't have a point at which the net electric field will be 0 because E1 will be always larger than E2. Here, I cannot have net electric charge equal to 0. Net electric field, sorry, I'm talking about net electric field, E, because I have two electric field pointing in the same direction. So also here, I don't have a solution. So the only solution should be here, okay, in this part here. Now let's solve it. That was just the physics of the problem. Now, if you want to solve the problem, now let's go. Net electric field at O should be equal to electric field due to 1 at O plus electric field due to charge 2 at O. And this should be equal to 0. Vector, of course. So what does it mean? At O, at point O, by the way, O is not the origin here. Let me call it P, it's better. Okay, at point P, P is the point at which my electric field is 0. The net electric field is 0. And as I said, P is somewhere here. So at point P, E1 P is equal to minus E2 P. The electric field created by charge 1 is equal in magnitude to the electric field created by charge 2, but opposite in direction. Okay. But in magnitude, they should be equal. Okay, now, in magnitude, what is the electric field created by charge 1? It will be K, absolute value of Q1 divided by the distance square. Let me call it X here. So P is at coordinate X, because that's what I'm asking you, right? What's the X coordinate? So the distance between Q1 and the coordinate X will be X, okay? I'm looking at this distance. So this is X. So here I have X squared. This should be equal to the electric field created by charge 2, which is K, absolute value of Q2, divided by the distance between point P and charge 2. And that distance is just this. Okay. So basically it's X minus 0.03 squared. So the K will simplify. So I will have what? Let's write it down this way. I will have X squared divided by X minus 0.03 square. This should be equal to absolute value of Q1 divided by absolute value of Q2. Okay. So absolute value of Q1, I know it already, 9, absolute value of Q2, 2.25. So this gives me what? Let me take, of course, the square root. I will have X divided by X minus 0.03 is equal to square root of this. If I take square root of this, it will give me 2. But here I will not choose, it can give you plus or minus 2. But I know that the minus will not be a good one, okay? So the plus is what is correct, because you see here, my X is positive. So X minus 0.3 is also positive. So here I have to take plus square root of 9 divided by 2.25. And basically this gives you square root, this gives you 2. Okay. Okay. So I have this is equal to 2. This is what I solve. So let me solve it, and I get X is equal to 0.06 meters. Okay. And 0.06 meters is just give you 6 centimeters. So this is my right solution. And this makes sense with what I said. So 0 is here. The origin is here. This is 0.3. My X is at 0.6. So I'm sure that it's somewhere here. Okay. So my point P is here at 0.06 meters, basically 6 centimeters. Okay. And I'm sure about this because I did the analysis before. Now, here, instead of taking the plus, which is the one that I got, which is the right one, and I know that it's plus because I know that if X is here, of course, this is positive and this is positive. Okay. If I took the minus one, what do you think? If I took the minus solution, I will get this one. I will get an answer which is between 0 and 0.3. Okay. So we already solved the problem. Now I'm just discussing. Okay. So for instance, here, if I said x divided by x minus 0.303 square is equal to plus or minus 2, basically plus or minus square root of this. I took the plus because I know that it should be positive. Okay, it should be here. If I took the minus, you can solve it. And you will find that x will be equal to 0.02 meters. So I will be here. 0.3 is here, 0.02 is here. But you see here, no way I can have what? Net electric field is equal to 0. So here, I will have electric field for created by 1 is equal to electric field created by 2, but they will point along the same direction. Okay? So here, this is not a solution. Net electric field will not be 0. They will be the same in magnitude, but it will point along the same direction, so it will not give you net electric field is equal to 0. Just to discuss this, because in the previous chapter as well, these type of problems are coming. Okay, where do I have net electric force is equal to 0? Okay? Good, and it will be always something like this. So the equality of the magnitude will give you two solutions. One in which both are pointing in the same direction, and this is not what I want because I want them to point in the opposite direction. This is one solution, and the second solution is basically the right one. One of them is pointing in the positive direction, and the second one is pointing in the negative direction, and they are equal in magnitude. Okay, so the same thing happened here. Okay, here I have Q1 here, which is equal to minus 5Q, and Q2, which is equal to plus 2Q. They are fixed on the x-axis, and the distance between them is L. And the question is, at what coordinate on the x-axis is the net electric field of the particles is equal to 0? So I want E net is equal to 0. Basically, is electric field created by 1 plus electric field created by 2. And you will do the same analysis. Okay. So let me do it for you. Okay. Here, now this is positive, this is negative, and this is positive. And you see, what's the direction of the electric field? Okay. For the green one, the electric field will be pointing towards always, the negative charge. So I have this here, and I have this, and I have this. For the red electric field, it's a positive charge, so the electric field will point away. So I have this, and I have this. All of them are pointing away. Okay. Now, of course, net electric field is equal to 0 means that the magnitude of electric field of 1 is equal to the magnitude of electric field of 2. Okay. But the right one is they should have opposite direction. So I will have two solutions for this condition. One in which they will be pointing along the same direction, which is this one. But that's not what I want. I want one in which they are pointing in an opposite direction. Okay. And that's what I want. And that's what I will solve, right? Okay. So that one will be where? Will be here. Okay. Good. Because here, I cannot have a solution because this electric field in red, green will be always larger, okay, than the one in red. So the solution will be given here, and the solution is, so the solution is this one, okay, basically this, okay. Not this one, because this one means this, that they are equal in magnitude, but the same direction. And here I know that for a fact, they cannot be equal. So there is no point here that has a net electric field equal to 0. Why? Because you see here, this negative sign, this negative charge is minus Q, minus 5Q. Okay. So the electric field created by the negative charge will be always in magnitude K, 5q divided by the distance. Let me call the distance square. And the electric field created by the positive charge would be k, basically absolute value of the positive charge, which is 2q divided by the distance square. And the distance will be what? The distance will be d plus L squared. And if you see here, this one will be always bigger, okay, than this one, because the charge is bigger, number one, and also the distance is smaller. So here I cannot have net electric field is equal to 0. Okay, so this is a solution here, and this is given by this one, not by this one. You got the idea. Okay. And the same thing goes for the previous chapter, where I was telling you the same thing, but where do I have net electrostatic force is equal to 0? And net electrostatic force was electrostatic force created by 1 plus electrostatic force created by 2, and you play with the distance. You will always have two solutions. One is physical and one is unphysical, because I want the net force equal to 0. Let's solve this problem here. So read the problem carefully. So this figure 2 shows two charged particles on the x-axis, and as you can see, this is my x-axis. So minus q is here at a position of minus 3 centimeters. So let me put it in meters, 0.03 meters. And plus q is here and at a position of plus 0.03 meters. And I give you, of course, one of them is 3.2 nanocoulomb and minus q is minus 3.2 nanocoulomb. So the question is, find the magnitude of the electric field produced at the origin. I'm looking for the net electric field, okay, at the origin. So the net electric field at the origin will be just the electric field created by minus q plus the electric charge created by plus q, and both of them at the origin. Okay, I'm looking at the electric field at the origin. So what is the direction of the electric field created by minus q? Minus q is negative. So the electric field will be pointing towards the negative charge. So this is electric field created by minus q. Okay. It's a negative charge. So of course, electric field will be always radially toward the negative charge. Okay. Now, what's the electric field created by plus q? So plus q is here, it's positive. So the electric field will be away, right? So let me just put it in another color here. So the electric field created by plus q will be like this. Electric field created by plus q. Okay, it's pointing away. So it will be like here. Okay, electric field created by plus q. It's pointing away from my positive charge. So my net electric field here, well, you know that these two will be equal in magnitude. So it will be just 2 times the electric field created by plus q at O. Now, what is the electric field created by? Because here, the electric field created by minus q at O will be just the same as same magnitude and same direction. It will be electric field created by plus q at O. Okay. They are equal in magnitude and same, pointing along the same direction, as you can see here. Okay, good. Let me get the electric field created by minus q or plus q at O. The magnitude will be k, absolute value of q divided by the distance square. And the distance will be just 0.03 square. You put it in meters because this k here is in SI unit. Okay? Is it clear? Good. The distance here should be in meters. Now I put the numbers, here you have 8.99, 10 to the power 9 SI. Now this Q is 3.2, 10 to the power minus 9. I put it in Coulomb, that's why I put minus 9 SI. And here the distance is just 0.03 meters square. And when you do that, you find that the magnitude will be 64, 10 to the power 3 Newton per Coulomb. So this gives you 64 kilonewton per coulomb. Okay, and that's the magnitude. Okay, now if I want to write it in direction, it will be just this. E net O, of course, will be just magnitude, but I know that it's pointing in the negative x direction. I'll have minus I hat. Okay. Very simple. Next question. So of course, this is the right answer. And the direction will be just in the negative direction. Let's go to the next question. So the next question is this. Let me just remove this. Okay. So the next question is this. An electric dipole with a dipole moment is given is this. Okay. So the dipole moment, P, this is P in magnitude, is directed along the positive x-axis in a uniform electric field, which is also in the positive x-axis. Now the question is, what is a change in the dipole potential energy? So I'm looking for change delta U, dipole, okay, not delta E, just delta U. The change in dipole potential energy when it is oriented 110-degree counterclockwise from the positive x direction. Let me draw a figure. Okay. So this is my x-axis. This is the origin. So I have a dipole. So the dipole, I have minus here, minus Q, and here I will have plus Q. And the dipole moment is pointing along the positive x direction. So the dipole, electric dipole moment, P, is pointing along the positive x direction, as it said here. And P, in magnitude, which is just QD, is 9.3 10 to the power minus 15 Coulomb meter. Now here I have an electric field, and the electric field also is pointing along the positive x direction. This is my electric field. And I gave you the magnitude and the direction. It's pointing along the positive x direction because here I have I hat, and the magnitude of the electric field is just 1.1 10 to the power 3 Newton per Coulomb. Now the question is, what is delta U, the change in the dipole potential energy? First, I know that if I have a dipole inside an electric field, what do I have? I have a potential energy. And the potential energy for a dipole inside an electric field is just given by minus P, which is a dipole moment, dot E. Basically minus P E cosine the angle between P and E. So here initially, theta initial is 0. Okay. So the cosine is 0. So basically my initial potential energy for my dipole is just minus P E. And I know P is given, let me write it here, 9.3 10 to the power minus 15 Coulomb meter. And then I multiply by E. E is given in magnitude, so 1.1 10 to the power 3 Newton per Coulomb. And I calculated this will give me the initial potential energy in Joule. Now, what is the final potential energy? As I said here, the final potential energy happens when now my dipole moment is going counterclockwise. So basically this angle here. Okay, so this is counterclockwise, of course, and the new angle theta final is equal to plus 110. So my new dipole moment is this. So this is plus, so basically this is P. So U final will be just minus P E cosine theta final. So I know P, I put the number, I know E, I put the number, I know cosine theta final, which is just 110. degree. Okay, don't forget to put your calculator in degree when you are putting the angle in degree. So the change in my dipole potential energy is just U final minus U initial. So it will be minus PE cosine 110 minus U initial, and I already calculated U initial here. So minus minus, so it will give me plus, okay, PE basically. So I put the numbers, of course. I know P is given by this. I know E in magnitude, and E is given by this. Okay. So I know this. So basically you calculate and you will get what? 1.37 10 to the power minus 11 joule. Okay. This is my change in dipole potential energy. And you see it's positive. What does it mean? That means that I have to apply a force to make it happen, because actually when my dipole moment is along the electric field, I have an equilibrium position, a stable equilibrium position. So I want to stay there. The dipole want to be aligned. The dipole moment want to be aligned with the electric field. Now, if I want to make it rotate it, I have to do an external work. Work applied is positive. Okay? That's why this delta U here is equal to work applied, and that's positive. Okay? The other way around will be negative. Okay, so if I started from here, the dipole moment will want to go naturally and be aligned with the electric field. So there, now, the work done by the dipole moment, that will be positive. Okay? And the work done by the external agent will be negative. I'll come back to this. But here, this work applied is positive because I want to go away from a stable equilibrium position. I have to do it by myself. Okay? Because the dipole moment want to be aligned with the electric field. Good. Now let's solve this problem here. Let's read it carefully and then we move. Let me just say that here, the delta U that we calculated is equal to what? Plus 1.37 10 to the power minus 11 joule. Okay. Good. This was just U final. Basically, U when theta final is 110 minus U initial when theta initial was 0. It was my initial state. Okay, so let me just remind you what we said in class. Work applied by the electric field is just minus delta U. And this will be minus this number here. Okay, and this is the work done by the electric field. Now the work that I'm applying as an external force, work applied, which is work done by the external force. So it's just plus delta U. Okay. I have to apply it. It's positive. Good. Now let's go to the next problem. So we have here an electron which is projected with an initial velocity of 3.5 10 to the power 6 I hat meters per second into a region of uniform electric field. The electric field is also along the positive x direction. The question is very simple. How far will the electron travel before coming to rest? So let's solve that problem. We have 2 ways or 3 ways to solve the problem. At least. Let's start by the first way. So here we have a 1-dimensional problem effectively because my electric, so this is my x direction. Let me plot it. This is my x direction. Okay. The electric field E is along the x direction. The magnitude of the electric field is 2.23 10 to the power 2 Newton per Coulomb. Okay. and it's along the positive x direction. My velocity v is 0 along y, and I have v naught x. So basically I'm along the x direction. So what is my v naught x? It's given 3.5 10 to the power 6 meters per second. Okay. So the handwriting looks terrible because I'm not used to this anymore. Anyway, but you get what I'm saying. Now it's a one-dimensional problem. So what will happen? It's an electron. What's the charge of an electron? The charge of an electron is minus E. Okay. So what will happen, of course, because the charge of the electron is minus E, and the electric field is going in this direction. So I have a force which is opposite. Okay, so the force here is going in the negative x direction. It's just minus E multiplied by E, because we know that the force is just Fe. Okay, QE. Here Q is negative, is this minus E, and opposite to the gravitation to the electric field. Good. So I can get my acceleration. As we said, the acceleration here will be along negative x, and it will be just what? So this is QA, MA, sorry. Okay, so the acceleration is just Q E divided by M. So Q here is negative, so I will have minus E divided by M. So effectively, I have a particle that have an initial velocity along x direction, subjected to an acceleration which is along the negative x direction. Okay? So v naught x is positive, but the acceleration is negative. So of course I will be decelerating. So this is the acceleration now. By the way, here I know everything. I know E. E is 1.6 10 to the power minus 19 Coulomb. I know mass of an electron is 9.11 10 to the power minus 31 kilogram. And I know the electric field, and the electric field is given by this. So effectively, I know what's the acceleration, and the acceleration is along negative x direction. Okay, how far will I travel before I come to rest? If I come to rest, my v will be 0. Okay, this makes sense. Moving in the positive x direction, acceleration in the negative, I am slowing down. I will eventually stop and then accelerate in the negative direction. So what can I do? I can apply v final square is equal to v initial square, which is v naught x square, plus 2a x final minus x initial. Okay. X final minus x initial is what I want. This is a d. V final square is 0 because I end up stopping. So ax I already know. So d, which is x final minus x initial, will be what? Will be minus v naught x square divided by 2ax. Okay. So this gives me minus v naught x square divided by 2. I know ax is just this. I will plug it here. I now have minus e divided by m. Of course, minus goes away because the distance is positive. And I know v naught x. I know 2. I know e. I know e. I know m. I calculate everything. This will give me a distance of 0.156 meters, which is 15.6 centimeters. Okay, which is this answer here. The other way to solve the problem is using the time. I can get the time first. Okay, I know that the acceleration is positive, so v at any time will be just v naught x plus acceleration along xt. So this gives me v naught x. I know the acceleration is just minus e divided by m multiplied by t. When I will stop, well, this vx will be 0. Okay, so vx is 0. So vx being 0, I can get the time. Okay, so what is the time? Well, easy. It will be just v naught x divided by e divided by m. This is the time at which I will stop. Now, once I get the time, what do? I know that x minus x naught is equal to v naught xt plus half ax t squared. Okay, so I know everything. I just take this time here and I will plug it here and I will get x minus x naught. Of course, this is faster, but this is another way to get the same thing, like in Physics 101. You remember Physics 101 very well? So this is just an application of Physics 101, but now I have electron, charged particle, can be positive or negative, and I give it an initial velocity, and you know the acceleration. Okay? You know how to, the kinematic and the dynamics of a charged particle in a fixed electric field. Okay. So let me solve the second problem, which is using the same idea. So at time t equals 0, a proton, now I know the charge of a proton is plus E, is projected in a positive x direction, in the positive x direction into a region of a uniform electric field. Now the electric field is in the negative x direction. Okay, so this is my x direction, and I have now E, which is in the negative x direction. Okay, I know the magnitude, by the way. The magnitude is just 5 10 to the power 5 Newton per Coulomb. But the direction is minus I hat, right? Negative x direction. Now, of course, my proton, which is positively charged plus E, is moving here. You see, in an initial V naught x, which is in the positive direction. That's what I said here. It's projected in the positive x direction. But it's subjected to an acceleration which is negative. Ax is negative. Okay. Now the question is, the proton travels 8 centimeters before coming to rest. What is the time interval over which the proton comes to rest? Now I'm asking you about the time. Okay, good. Well, you know how to do this, right? So basically, you have Vx at any time will be V naught x plus axt. But by the way, what is ax? Ax is negative, right? Ax is just q e divided by m. And here q is positive plus e. But e is negative, okay? E is going in the negative x direction. Okay, so ex is negative. The magnitude is positive, of course, but ex is negative. So minus ex divided by m. So the acceleration is just minus ex divided by m. Okay, ex being this, ex is equal to magnitude of e. Okay, and the minus is giving me the direction. So I will have what? V naught x minus e divided by mt. When I come to rest, of course, my Vx is 0, so this should be 0. And the time will be what? V naught x divided by e divided by m. But the problem here, I did not give you directly V naught x. So how do we get V naught x? Well, I gave you this distance here from here and before coming to rest. You use the second equation. So V naught x, you will get it using V final square is equal to V initial square plus 2 times acceleration multiplied by x final minus x initial. So V final square is 0. So I have V naught x square. I have here 2a, of course, a is negative, so it will be e divided by m multiplied by d. So here I know everything. Okay, so I know what is V naught x. V naught x will be just plus or minus, but I will choose a plus because V naught is along the positive x direction. It will be just square root of 2e divided by m multiplied by d. Now this is my V naught x. I'll just plug it here and I'll get my time. So the time will give you 58 nanoseconds. Don't forget, nanosecond is 10 to the power minus 9 seconds. Okay, so if you put everything in SI unit, you will get the final answer in SI unit, which is a second. And then you put it in nanosecond. Okay, so again, here put everything in SI unit. Clear? Okay. So here, of course, this mass is not mass of electron as before, it's the mass of the proton. The mass of the proton is in your formula sheet. What is the mass of the proton? 1.67 10 to the power minus 27 kilogram. It's in your formula sheet. Okay. Mass of electron is also in your formula sheet, 9.1 10 to the power minus 31 kilogram. Okay, good. Next question. So we have 2-point charge, Q1 that has this charge and Q2 that has plus this, okay? So Q1 is minus 5 nanocoulomb and Q2 is plus 5 nanocoulomb. And they are separated by a small distance of 3 millimeters. They form an electric dipole, okay? So these two are forming an electric dipole. Yeah? Now let me put it this way. So let's assume that they are on the positive, on the x-axis. So this is my origin. So minus Q1 is here, and Q1 is equal to minus 5 nanocoulomb, and Q2 is here, and Q2 is plus 5 nanocoulomb. And the distance between them is 3 millimeters. You put it in meters, 3 10 to the power minus 3. Okay. So the origin is right here in the middle. So here you have 1.5 millimeter, and here you have 1.5 millimeter. So what is my electric dipole moment? My electric dipole moment goes from the negative to the positive. So this is my electric dipole moment, P. So it will be equal to just Q D, D being the distance going from the negative to the positive charge. So D here is just plus 3 10 to the power minus 3 meters I hat. Good. Now, these charges are in a 500 Newton per Coulomb uniform electric field whose direction makes an angle of 37 degrees with a line connecting the charge. So the line connecting the charge is the x-axis. Now my electric field, let me draw it in another color. The electric field is in this direction here. Okay. E is in this direction. And the direction of E, my drawing is not very realistic, so let me just erase this. So E is in this direction. And the angle between E and P is 37 degrees. Okay, let's assume that this angle is 37 degrees. Okay. So E is constant and E is in this direction, and it's making an angle of 37 degrees. Now the question is, what is the magnitude of the torque exerted on the dipole? You know that when I have a dipole inside a constant electric field, the dipole has a torque on it. Okay? The dipole wants to align with the electric field. Okay? And when they are aligned, that's a stable equilibrium position. Okay? Now, before they are aligned, I have what? A torque that is acting on the electric dipole. So that torque will make my dipole rotate and make it align with the electric field. So that torque, as we just said in class, that torque is just the dipole moment, electric dipole moment, cross the electric field. So what's the magnitude of the torque? It will be, of course, magnitude of P multiplied by magnitude of E, sine the angle between E and E, which is theta here. So what is the magnitude of P? Magnitude of P will be just Q multiplied by D. Magnitude of E is E, and sine theta is sine 37 degrees. So I know Q. What is Q here? Q is this, is 5 nanocoulomb. So 10 to the power minus 9. You put it in coulomb. Distance you put it in meters. Everything should be in SI units. Okay. So distance should be in meters. So distance is 0.003. Okay. Basically 3 10 to the power minus 3. And E, what is the electric field? 500. and then you put your sine 37 degrees. When you do it, of course, don't forget, okay? Your calculator should be in degree. Okay? If it's in radian, you change it in radian. So basically, in degree, this is what you will have. Okay? 4.5, 10 to the power minus 9 Newton meters. Okay? Again, when I have a dipole moment, electric dipole moment, put in an electric field, the torque is just P plus E. Okay? The dipole moment wants to align with the electric field. And I told you about the potential energy is just minus P dot E, okay? Which is minus PE cosine theta. And then I told you that the work done by the electric field, if the dipole go from theta initial to theta final, theta initial to theta final, the work of the electric field will be just minus delta U. And the work that I apply will be just plus delta U. Okay? This is just a summary of what we did in class, and you will apply it in many problems. Now, let's apply it to this problem, for instance. Okay, so here what do we have? We have an electric dipole consisting of charge of magnitude this. That means I will have minus 2 microcoulomb and plus 2 microcoulomb separated by 6 micrometers. And then I put this dipole in an electric field of strength 1000 Newton per Coulomb. Initially, the dipole is parallel to the field. Initially, I am in the stable equilibrium position. So the stable equilibrium position is when the dipole, here you see the dipole is here from minus to positive, and it's along the electric field. Okay, so I'm happy. This is stable equilibrium position. I don't want to move out of this. Okay. The question is, in this orientation, in this configuration in which P is aligned with E, what is the torque? The magnitude of the torque. Well, here you know that P is aligned with E. Okay, so gross product will give you 0. So the magnitude will be 0. Why? The sine theta is 0 because theta is 0. Okay? A cross product is 0 when the two vectors are aligned or anti-aligned. But here they are aligned, so the torque is 0. And this tells you that once I'm aligned, once the dipole is aligned with the electric field, there is no torque now. He wants to stay there forever and ever. Now, if I want to rotate it, I have to do a work. And that work should be positive. And that's the next question. How much work is required to rotate the dipole from parallel to anti-parallel? I'm going from theta initial, which is 0. And by the way, this was a stable equilibrium position. Okay. To theta final, which is 180 degrees. So what is the work? Of course, you know that work applied is just plus the change in dipole potential energy. So work applied will be U final minus U initial. But what is U final? Of course, U, as you said, so U final minus U initial. U, as we said, is just minus PE cosine theta. So you just replace, of course, theta by theta final. And then theta initial, you replace it by 0. Okay. So theta final is this. We put it here. And you see this is plus PE because cosine 180 degrees positive is negative, minus is plus. E initial is this. Okay. And you take the difference and you see that the work applied will be this. Again, let me start again. This is my initial state. And you see the potential energy is minus PE. This is a minimum potential energy. That's what we call a ground state. Okay. It's a minimum potential energy. This is my stable equilibrium position. I am there. The torque is 0. I don't want to move out of there. Okay. But here I force the dipole to go 180 degrees. Okay. So it goes there. It goes to the maximum potential energy. And by the way, here the torque is 0, but also here the torque is 0. But this is unstable. Okay. As I said in class, this is the top of a hill. And this is the bottom of here. This is the bottom of a valley. Okay. Both of them are stable, equilibrium position. This one is stable and this one is unstable. Okay. And the work that I have done is just U final minus U initial, which is 2 times PE, and I got it already. Next. Now let's solve this problem here. A certain electric dipole is placed in a uniform electric field of magnitude 10 Newton per Coulomb. The magnitude of the torque on the dipole, plotted as a function of the angle between E and P, basically, angle theta is shown in the figure. So how much work is needed by an external agent to turn the dipole from 30 degrees to 60 degrees with respect to E? So the question is, what is delta U? Because I know that work applied is plus delta U. Work done by the electrical is minus delta U. But here I'm looking for work done by an external agent, so it's plus delta U. So it gives me U final minus U initial. Basically, U final is U when theta final is equal to 60 degrees, and U initial is U when theta is equal to 30 degrees. So I know U, by the way. U is just minus PE cosine theta. So the work that I'm looking for, work applied, okay, will be just, I can put here minus PE as a common factor. So if I have minus PE cosine 60 degrees, so here I will have minus sine 30 degrees. Okay. This is the work that I'm looking for. But the problem is I don't know what is PE. I did not tell you what is PE, but I gave you even better. I gave you torque as a function of theta. So you know that the magnitude of the torque is just PE sine theta. And you see, the torque is just a sine function multiplied by a prefactor. And you see here, this is a sine function. At 0, I'm 0. At 180, I'm 0. At 90, I'm max. Okay. So this torque is proportional to the sine theta. Okay. Good. Now, at theta, which is 90 degrees, the torque is just PE, because sine 90 degrees is equal to 1. Okay. So this is 1. So this torque here, which is given here, torque at theta is equal to 90 degrees, is just equal to PE. So now let me read it here. It will be just 50 10 to the power minus 2 Newton meter. Okay, this is PE. Now I know PE. Let me plug it here. Okay, so I will have what? Minus half. This is just minus half. This is half. Cosine 60 degrees minus sine 30 degrees. And this will give you exactly this answer. Okay. So we have exploited the graph and we have exploited all the data of the problem. You got the idea? Okay, now let me move to the next problem. So let me move to the next problem. Before that, let me erase this. Okay, and this is what I did here. Okay, same solution. Okay, this is the solution here. So whenever you have a problem, respect yourself, meaning respect how you think, how you naturally solve problems. This is you, okay? And you know yourself better than anybody. So whenever you have a problem, think and start. And then you start solving it. That's your natural way of solving problems. And then you look at my recording or the solution that I gave you, or you remember in class how I solve it. And then now you can see, oh, okay, from that, how I can improve my way of solving problems. Okay, don't just go watch the solution directly. You will not learn much, but do it yourself. And you see that, okay, this is my natural way of solving problems. Now, how can I improve it? Okay, this is the data that I did not take into account. I can incorporate it here. I can go faster here. Okay, etc., etc. Okay, and that depends on each student. That's why I'm going slow here. Okay, next. let's solve the next problem. Okay, so let's read it. What do we have here? In this figure, we have this 0.3 gram metallic ball hangs, wait a second, from an insulating string in a vertical electric field directed upward as shown. So, okay, so this is my metallic ball. It has a mass m, and m is equal to 0.3 gram. You put it in kilogram, of course, because I want to put everything in SI units. Good, it's 3×10⁻⁴ kilogram. Good. Now it has a charge Q as well, but we'll come back to that just in a second, because it's a metallic ball in an electric field. Okay, the electric field is given. The magnitude of the electric field is 4,000 Newton per Coulomb and directed upward. So the question is this: calculate the charge Q of the ball if the tension in the string is given and it's equal to 0.005 Newton. You see, when I was having a proton, an electron, I was neglecting what? The gravitational force. And I was neglecting the gravitational force because the gravitational force is negligible compared to what? Electrostatic force. That's why in my problems before, you remember here, where is it? In all these problems, you know, my acceleration is just due to what? The electrostatic force. Okay? These are the problems that we already solved before. Okay? So I did not talk about gravitational force. Why? Because the gravitational force, Fg, which is mg, is very, very small compared to what? Electrostatic force. And electrostatic force is QE. Let me take everything in. Absolute value. And why is this? Why is this? Because mass of electron is very small. What's the mass of electron? 9.1 × 10⁻31. And mass of proton is also very small, okay? 1.67 × 10⁻27 kilogram. These are very small. So I did not consider the gravitational force. Now in this problem here, I need to consider the gravitational force. Why? Because the mass I'm giving you now is not negligible. Yeah, it's not 10⁻27 or -31. It's 0.3 gram. Now the gravitational force and the electrostatic force have roughly the same order of magnitude. Okay, you know, you have a difference, but it's not that huge. Now here, now I have to consider what? The gravitational force. It's not negligible. I cannot ignore it. Okay? So here on my ball here, of course, I will have the gravitational force pointing downward, Fg. And what is the magnitude of the gravitational force? Is just mg. Let me calculate it. So mg, I know m, 0.3 gram. I put it in kilogram, multiplied by g, 9.8. And this is what? This is my gravitational force, 2.9 10⁻³ Newton. So I know it, 2.94 10⁻³ Newton. Good. Second, now I told you that there is a tension. So the tension here is up, right? Because I have a vertical string, it's insulating. So the tension is up. So if there was no electric field, what will happen? Of course, the gravitational force will be equal in magnitude to the tension force because I'm in equilibrium. Net force is equal to 0. Okay? If there was no electric field, this tension force here will be exactly equal and opposite to this gravitational force. Same magnitude, but opposite direction. If there is no electric field or no charge on my metallic ball. But here I have a charge, so I'll have electrostatic force. And here you see something, my gravitational force is larger than the tension force. Okay? That means that I have a third force, which is an electrostatic force, which has to add to the tension force, okay, such that overall I will have, which has to add to the gravitational force, such that, so here, yes, I made a mistake there. Okay. Actually, the tension force is bigger than the gravitational force. Yes, that's what I'm saying. Okay. Tension force is bigger than the gravitational force. So basically, my electrostatic force has to add to the gravitational force such that the net force along y is 0. So here I know that the tension force is up and it's equal to 5 10 to the power minus 3. And I know that the gravitational force is down, is 2.9 10 to the power minus 3. So I know for a fact that my electrostatic force should be down. Okay. It should be down. That means that my charge should be negative because E is up. Q should be negative. Q and E should have the negative signs. Okay. So basically Q is negative. That's number one. But also my electrostatic force is down. So, but still I have an equilibrium. So along the y-axis, if I project, I'll have plus T minus mg minus QE is equal to 0. So now I will get what is Q. So Q will be the difference between the tension force and the gravitational force. Then I divide by the electric field. So this type of problem will come again and again and again. And here I will get my Q, which is equal to minus 5.2 10 to the power minus 7 Coulomb. And the charge is negative. Okay. Good. If on the other hand, if the gravitational force was bigger than the tension force, now, what do you think? Of course, the gravitational force is bigger than the tension force means that the tension force needs the electrostatic force. So the tension force and the electrostatic force will be pointing upward. Okay. That means that QE is upward. That means Q is positive. Okay. So we will play with this. Okay. But don't forget, we always have equilibrium. So the net force is equal to 0. Now let's go to the next problem, which is a little bit more interesting. So let's read the problem. We have a charged particle. Let me just put it this way. Okay, so we have a charged plastic ball, okay, not a particle. We have a charged plastic ball of mass 1 gram. You put it in kilogram, of course. So mass is 10 to the power minus 3 kilogram. Suspended on a light string in presence of a uniform electric field, and the uniform electric field is given. I give you the magnitude and the direction, okay? But here I give it everything in unit vector notation, okay? So it's 3 10 to the power 5 I hat, 5 10 to the power 5 j hat Newton Coulomb. So the electric field is pointing in this direction, okay? So 3 10 to the power 5 along this direction, and then 5 10 to the power 5 along the j direction. So my electric field is given by this, as you can see. Now the ball is in equilibrium. This is very important. Equilibrium means net force is equal to 0. Net force on ball is equal to 0. Okay, so the ball is in equilibrium when Q is equal to 40 degrees. Find the charge on the ball. Good. So first, let's have the inventory of forces, okay? Of course, I will have gravitational force downward. That's number one. I will have tension force, and tension force will be along the string. And then I will have what? Electrostatic force, because the ball is charged, and that charge is in an electric field. So electrostatic force F is just QE. Okay, good. And the question is to find Q. Good. I will use, of course, equilibrium. So when I have equilibrium, net force is equal to 0, meaning gravitational force plus tension force plus electrostatic force is equal to 0, or electric force is equal to 0. So what I will do, I will choose my axis carefully, X and Y axis. Okay. So this will be my X axis, like in Physics 101. This will be my Y axis. So net force is equal to 0. That means net force along X is equal to 0. So what is my net force along X? Okay. Now let's get our net force along X. We can get it simply. So if this is my X axis and this is my Y axis, net force along X will be what? It will be 0. Now let's start by the gravitational force. So this is my X axis. Gravitational force along X is 0. Good. Now tension force along X. You see here, this is a tension force. And along X, this will give me. Okay. So it will be minus tension force. Now sine theta. And theta is equal to 40 degrees. Okay. So I'm looking at this component here. So it's negative, right? Minus T sine theta. Now, electrostatic force along X. So I need to get what is this angle here. But do I need it? Not really. Because here you see my electrostatic force will be Q multiplied by E. Okay. So it will be Q. Now what is E? E we already know. Is 3 10 to the power 5 I hat plus 5 10 to the power 5 j hat. Okay. So this will give me plus Q multiplied by this gentleman here. So 3 10 to the power 5. This will give me Fx. Okay, this gives me Fx. And this should be equal to 0. So I have my first equation. So this is what I did here. Okay. This is what I did here. I have my first equation. Now along Y, let's do the same. Gravitational force along Y is just minus mg. Tension force along Y will be plus T cosine theta. Okay, because I need this gentleman here. So it's plus theta cosine theta. Okay. Now, what is the electrostatic force along Y? Well, I know it here. Okay, it will be plus Q times 5 10 to the power 5. And this should give me 0. Okay. Remember, this Q multiplied by this will give me the component of the electrostatic force or electric force along X, and Q multiplied by this will give me the component of the electrostatic force along Y. So now I have my second equation. Okay. So as we said, okay, this is minus mg, this is plus T cosine theta, and this is Q EY, EY being this number. I mean, yes, and EX being this number. So I have my second equation, two unknowns. So here, what are the unknowns? The unknown are the charge and the tension. Unknown are charge and tension. And you know how to solve a system of two equations with two unknowns, right? Substitution, addition, you know the method of solving a system. So this will give you the charge, which is here. And I know that the charge is positive. Why? Because you see the electrostatic force has to be aligned with the electric field. So that means Q is positive, F is QE. Okay, Q should be positive because in order to generate this deflection angle, I need a force which is along the x-axis, along the F, which is along the electric field. Okay? And then this is my Q. Now T, that's another question, okay? Get me T. It's a system. You get Q, you get T, you get T, you get Q. Okay? So get me T. Now something else. What happened if Q was negative? If Q was negative, what will you have? Think about it. Now let's finish by this problem here. What time is it? Okay, let me stop here. This problem, we will solve it in class, inshallah. Okay. So check it out and look at it. We'll solve it in class, inshallah. Thank you and enjoy. Assalamu alaikum.